In the cosmic silence that surrounds us, amid the infinite expanses of stardust and ancestral radiation, there lies a question that never ceases to haunt us. Are we alone? For millennia, we have lifted our gaze to the stars, searching for a reflection of home in a universe that seems as hostile as it is fascinating. And yet, among the billions of stars scattered across the night sky, there is one, small and discreet, that captures the attention of scientists like few others. Proxima Centauri. It is neither bright nor striking. It is a red dwarf, one of the most common stars in the galaxy, and yet it harbors a mystery that could rewrite our understanding of life in the cosmos. At just 4.24 light-years from Earth, Proxima Centauri is the closest star to our solar system. But that is not its most fascinating feature. In 2016, astronomers discovered a planet orbiting it, Proxima b. From that moment on, humanity began to look at that tiny speck with new eyes. Not because it is the largest planet, nor the most exotic, but because it might be the most similar to our own. A rocky world, comparable in size to Earth, located in the habitable zone of its star. Potentially, an oasis in the middle of the cosmic desert. But what does habitable zone really mean? It is not enough for a planet to be at a distance that allows the presence of liquid water. There are multiple factors to consider: the composition of the atmosphere, the intensity of stellar radiation, the presence of a magnetic field, the stability of the orbit. In other words, a most delicate balance. Proxima b moves within this fragile boundary, completing an orbit in just 11.2 Earth days, at a distance of only 7 million kilometers from its star. A distance that, compared with the 150 million kilometers separating Earth from the Sun, would suggest a scorched, uninhabitable world. But Proxima Centauri, being a red dwarf, emits only a fraction of the light and heat of our Sun. This is the key that allows the planet to fall within the habitable zone, at least in theory. However, the conditions on Proxima b are far from simple. One of the most intriguing aspects is its synchronous rotation. Like the Moon with Earth, it always shows the same face to its star. This creates two radically opposite hemispheres, one in perpetual daylight, the other shrouded in eternal icy night. Yet it is precisely in this dichotomy that life may lie hidden. Scientists hypothesize the existence of a twilight zone, a narrow belt where the temperature could be stable enough to allow liquid water. In that strip of land between light and darkness, rivers might flow, lakes might form, and elementary life forms might grow. A kind of climatological oasis on the frontier between extremes. Supporting this hypothesis are simulations suggesting that water, accumulated as ice on the night side, might melt at the boundary with the temperate zone, fueling a rudimentary hydrological cycle. But water alone is not enough. An atmosphere is needed to retain it and protect it from violent stellar radiation. And here the picture becomes more complex. Red dwarfs, though long-lived and stable on cosmic timescales, are notoriously magnetically active. Proxima Centauri is a true factory of flares. Sudden bursts of energy that can increase ultraviolet radiation intensity by up to 14,000 times in a matter of seconds. Such a storm on our planet would cause catastrophic damage to power grids, satellites, and perhaps even to the biosphere itself. In 2018, a flare from Proxima Centauri released an amount of energy 100 times greater than the most powerful event ever recorded on the Sun. If such an explosion were to strike Proxima b directly, the planet's atmosphere would be severely tested, if not stripped away entirely. However, there is a fascinating hypothesis that could save this world's fate. If Proxima b had a liquid metallic core, similar to Earth's, it could generate a magnetic field strong enough to deflect much of the harmful radiation. This invisible shield, if present, would be the first essential requirement for the survival of any complex form of life. But the questions do not end there. Where would Proxima b's water come from, if it indeed exists? Some researchers hypothesize that the planet did not form where it is now, but much farther from its star. In that case, it could have accumulated a huge amount of ice, perhaps up to 10 times more than Earth. Later, gravitational migration would have brought it to its current orbit. Even if stellar radiation had eliminated 90% of that reserve, enough would remain to form vast liquid oceans, concentrated precisely in the twilight zone of the planet. All this makes Proxima b one of the most promising candidates in the search for habitable worlds. But how can we know more when it is over 40 trillion kilometers away from us? For now, we are still bound to indirect observation methods. Proxima b, for example, was not discovered through the transit method, like most known exoplanets, but through radial velocity. In practice, scientists detected tiny oscillations in Proxima Centauri's motion, caused by the planet's gravitational pull. These oscillations, analyzed with extreme precision, allow them to deduce the mass and orbit of the orbiting body. A task so delicate it is measured in variations of just a few centimeters per second. But if our eyes cannot yet see Proxima b directly, humanity's ears have nonetheless tried to listen. In a case that made headlines around the world, the Parkes radio telescope in Australia detected a narrowband signal coming from the direction of Proxima Centauri. The signal, nicknamed BLC-1, seemed to have all the characteristics of an artificial message. Speculation exploded. Was this the first contact with extraterrestrial intelligence? However, subsequent analyses revealed it to be terrestrial interference, a cosmic illusion born from the complexity of our own instruments. Yet the fact that such a signal could deceive even the most skeptical experts shows just how little we still know. And in the meantime, new and bolder hypotheses are beginning to take shape. Because if a rocky planet can have water, an atmosphere, and a temperate zone shielded from radiation, then it can also host complex chemical reactions. And when chemistry meets time, the impossible becomes merely a matter of probability. Some computer simulations have tried to model Proxima b's environment by hypothesizing different atmospheric compositions, and the results have been surprising. In at least 1 out of 3 scenarios, thermal conditions would allow not only the stability of liquid water but even the formation of climate cycles similar to those on Earth. Cycles in which evaporation, condensation, and precipitation alternate, creating a true meteorological system. A hypothesis which, if confirmed, would make the planet not just habitable but actively livable. Yet we cannot ignore the invisible enemy, time. Red dwarfs like Proxima Centauri may be long-lived. They can shine for trillions of years. But in their first billions of years, they emit enough radiation to sterilize any unprotected planetary surface. The real question, then, is not just whether Proxima b can host life today, but whether it was ever able to develop it. And if it did, in what form? Some astrobiologists propose the idea of internal, subterranean ecosystems, shielded from radiation by thick rocky crusts. As with extreme life forms found in Antarctica's subglacial lakes or in the deep oceans of our own planet, life on Proxima b might have adapted to radical conditions, far from the surface. But the most fascinating speculations come from yet another perspective. What if we were not the first to observe Proxima b? What if, millions of years ago, a technological civilization had already reached its surface, building structures, colonies, perhaps even leaving hidden signals in the landscape? Science fiction, perhaps, but no less rational than the hypotheses guiding today's research. The truth is that interstellar exploration, however distant, is no longer pure imagination. Theoretical projects like Breakthrough Starshot propose sending tiny probes equipped with solar sails, accelerated to relativistic speeds by powerful Earth-based laser beams. According to calculations, such a probe could reach Proxima Centauri in just over 20 years. A short time on a cosmic scale, but an unprecedented technological and engineering challenge. And if one day we truly managed to send one of these electronic eyes to fly over Proxima b, what might we expect to find? A sterile expanse, scarred by craters and electromagnetic storms? Or perhaps, and here the mind ignites, a dark and living landscape of red skies and misty oceans, swept by eternal winds and inhabited by creatures invisible to our eyes? Science today cannot answer with certainty. But it can dream with rigor. And this, precisely, is the heart of space research: to walk the boundary between what we know and what we cannot yet even imagine. And yet, amid these hypothetical scenarios, reality often breaks through with its harshness. In recent years, rumors spread that the James Webb Space Telescope had observed a sea of lights on Proxima b, a possible alien metropolis seen from space. The news caused a stir, igniting the fantasies of millions. But as so often happens, the truth was very different. The lights observed did not come from Proxima b at all, but from an entirely different object, a brown dwarf named W1935, in whose atmosphere a natural, explainable methane emission was recorded. No city, no civilization, only a misunderstanding magnified by our natural yearning for wonder. Even the BLC-1 radio signal, which for a brief moment had raised hopes of an alien message, turned out to be nothing more than terrestrial interference. But these false positives are not failures, they are steps forward. Every time a theory is disproved, our method improves. Every disappointment teaches us to build better instruments, to ask smarter questions, to look further. This is how knowledge is built. In the meantime, however, discoveries do not stop. At least 2 other planets have already been identified in the Proxima Centauri system: Proxima d, a small world with just a quarter of Earth's mass, and Proxima c, perhaps a mini Neptune or an icy super-Earth. The possibility that the system hosts other still invisible planets, or that complex gravitational interactions create orbital stability conditions ideal for the development of life, remains open. In particular, the fact that Proxima b is located in a multiple planetary system offers intriguing scenarios: exchanges of matter between planets through cosmic impacts, the possibility of local panspermia, or even orbital migrations that may have altered environmental conditions over the millennia. In this mosaic of data, hypotheses, and observations, Proxima b continues to elude a definitive definition. It is a natural laboratory, a cosmic experiment, an enigma carved into the red light of a distant star. And yet, it is precisely in its ambiguity that its strength lies. Because as long as we do not know for certain what lies on its surface, we can continue to imagine. We can continue to search. We can continue to hope. Perhaps, one day, the first non-terrestrial footprint will be left right there, among the twilight rocks of Proxima b, and perhaps, turning back, whoever sets it will see in the sky a tiny distant blue dot, our Earth, and understand, for the first time truly, how fragile and precious the world we come from is. If you've made it this far, it means you love curiosity as much as we do. If you enjoyed this journey, leave a like, write a comment, and subscribe to the channel. It's the best way to support what we do. Your presence truly makes a difference. Until the next exploration.